And we went through the meaning and understanding of this interaction diagram, that you are going to have this relationship between the axial force, the axial load, the strength, and the moment also strength. We discussed this eccentricity and the meaning of the small eccentricity. Small eccentricity, when you have the eccentricity is going to be about 5% of the beam length, which at this point here, the small eccentricity, which is right at this point. And we went through an example, and also our understanding that this is going to be the envelope for the strength. And for any load combinations between the moment strength and the axial forces strength, if it's going to be within this envelope, your column should be fine, or structural member. If it goes up beyond or out of this envelope, it means it's going to be unsafe. So when you bring here the two forces as rotational force, which we call here the moment, and axial force as a demand, and you can plot here a point. Let's say the point turned to be right here at this location. Based on the given moment and given axial load, it means that your structural member is okay with this given load combination. But if I have the load demand, which means axial force demand, which I have from here, I'm going to say here's the axial force demand. So this is going to be here the demand. And you're trying to find out the maximum moment that goes with it. So what you need to do is to draw a straight line for this demand, and then you go down, and with that you can figure out the maximum moment that this column is going to be able to support. Which means in this case, it's going to be the demand, it's going to be the capacity. Or if you have the amount of applied moment on the column, and let's say it's going to be here, here's applied moment on the column. You draw a vertical line. Once it hits this envelope, you can go horizontally, and this is going to be the axial force strength that goes with this given moment. Does it make sense? The difference between the two? Or no?
Yeah, it makes sense.
Okay, thank you. Who did this example?
Professor,
Yes.
on that last diagram you had,
Yes.
so is that box that you have between 300 kips and 600 kip per foot, is that what we're trying to achieve, or just at that point?
That was just an example. That was example that was discussed last time.
Okay.
That was just quick numerical example that I went through there. But all of these values going to be just values that is going to be based on each problem, right? Each problem is going to be different.
Mm-hmm.
Okay.
Okay.
Now in this example, we have three cases for this given column. The first one, it says when you have a small eccentricity, meaning that you're going to be using, and this is going to be case A, you're going to be using the already known simple example or simple equation that we have here. So this equation here, it works great when you have only axial force, or axial force and small eccentricity of 5% of H. 5% means you're going to bring it here for the eccentricity to be 10% of H. What does it mean by 10% of H? It's going to be 10% of the 20 inches. So it's going to be 2 inches amount of eccentricity in this case. It's going to be maximum of 2 inches here for this dimension. So in this case, to solve the first item, what you need to do is just find out VPN. Once you have this VPN, you have the maximum eccentricity that goes with this equation. You're going to be taking 10% of H, the 2 inches, multiply here 10% by 20, it's going to be 2 inches. So you divide this by 12 to put it in feet, multiply by VPN, it's going to be the moment that goes with it. So with 672 in this example, you're going to have your 112 kip foot. Meaning, if your axial demand, don't forget this is now capacity, right? It's going to be a capacity point that goes together for the same point. Meaning, if you have an axial demand, which means applied force here, is going to be equal to 672 kips. The amount of moment that this column is going to be able to support ranges from 0 to 112 kip foot. And in this case, we're going to be along this line here. When the axial load is going to be 672 kips, you're going to have a capacity that goes from 0 all the way to 112 kip foot. Or if the moment demand is equal to 112 kip-foot, which means right here, your axial force can be anywhere from 0 to 672 kips as a capacity. That was the first item, item A. Comes to item C here, I'm gonna just jump to item C because B is gonna be kind of a little bit longer. So I'm gonna jump to the easy one, which is item C, when you have this balanced strain. What's the balance point? Balance point is gonna happen when the concrete strain is gonna be at 0.03, and the steel tension is gonna be right at the yield point, which means it's gonna be at 0.0021 or 207 if you like. Here is gonna be 0.002. So I'm gonna jump here to case C or item C, balance condition. In this case, we're gonna put the concrete strain to 0.03. The strain in tension steel is gonna be 0.02. With that, you should be able to figure out the strain at the compression steel. From this symmetry, you have two similar triangles, and with that, you can find out absolute prime. Absolute prime, based on this analysis, we find it to be 0.0021. It's almost or nearly right at the yield point, and this is good. It's gonna make our life easier in analysis. Now I'm gonna have here three forces applied on the system. First one is gonna be a tension force. It's gonna be equal to F sub Y because it's already at yield, multiplied by AS at the bottom. Gonna have one compression force based off the concrete stress distribution. It's gonna be 0.85 F prime C times the depth A times the width, which is 14 inches. Third force is gonna be the compression of the steel. It's gonna be also F sub Y multiplied by this AS. I have one external force. This C1 plus C2 is not equal to the tension force, like in the past. In the past, we didn't have any axial forces. It was just a section exposed to moment. And for that, we said the C1 plus C2 equals to the tension force. Now, in this case, we're gonna say external force is gonna be equal to C1 plus C2 subtracting T. Okay, let me see what happens. Here's the C1 value, numerical value. C2 is gonna be also numerical value because all the strains are determined for us. And the tension force also, we have it as numerical values. We have 3 number 9 multiplied by 60 case size, gave you 180 kips. Now, when you take here 413 plus 170, subtracting 180 is going to give you the external applied force, like as a strength. This is going to be PB. The difference, 413 plus 170 subtracting the 180. Now, the eccentricity that you have there, if you like, you can just take the moment about this point. Take the moment about this point for the internal forces and set it equal to the moment at the same point for the external forces, and they're going to be equal to each other. So in this case, you take the moment about this point, you say C1 times, you can call this Z1, plus C2 times Z2 equals to, now look at this, it's going to be equal to the eccentricity plus 7 inches. Why this 7 inches? Because this goes to the mid-height of the column. And from here to there is going to be 7 inches. Don't forget, from here to there is going to be 14. So it's going to be half the way. So it's going to be 7 plus EB. Of course, you're going to divide this by 12 to put it in feet, multiply by this external force. Now, once you set this two moments equal to each other, which means moment of the external force is going to be equal to the moment of the internal force, you set them equal to each other. Now, in this case, you can solve for this eccentricity. Don't forget that for this case here, you have two unknowns. You have the axial force, external, and then you have the eccentricity. Axial force, you're able to determine it when you say summation of the force in the x direction equal to 0. You put all the internal forces to be equal to the external. With that, you're able to find out this axial force. Now, for the eccentricity, we simply take the moment about one of these points so that we can figure out this EB. Now, we're able to solve for this E. Now, how about the moment? You say moment is going to be equal to PB multiplied by the eccentricity. This is going to be the moment. So with that, you are going to have the second point in our analysis, which is this point here, right? When the strain is going to be equal to, in the steel, equal to 0.02, you're going to have 2 points. This is going to be the axial force, which means the Y component, and this is going to be the X component, which is the moment component along this axis. So great. Now let's look here at the last one. Last one, it says when the eccentricity equals to 5 inches. Just eccentricity is given. So I'm going to say in the previous problem here, all the strains were given, and we had two unknowns. one of the unknowns with the amount of axial force. I'm just gonna jump to it for quick back. Because the strains were determined, it means all the internal forces were determined. And then we add here two unknowns. One of them is gonna be this axial force, the other one is gonna be the eccentricity. Axial force times eccentricity is gonna be the moment, which is the x-axis. On the y-axis is gonna be just this PV, which is the axial force. So when you have all the strains predetermined for you, because we have a specific case, when the concrete strain is gonna be at 0.03 and the tension the steel is gonna be at 0.02. Now with that, we have two unknowns, and we're able to do them by doing summation of the force in the x equal to 0, and summation of the moment about one of these forces gonna be equal to 0. So we're able to solve for these two unknowns. Now let me go here to case B, see what do we have and what is missing. We don't have all the strains. This is not determined yet, right? And when it comes to external, we don't have the axial force, but we have the eccentricity. See what happened? In the balanced section or balanced point, we didn't know the eccentricity, we didn't know the axial force, but we knew all the stresses. Now in this case, we don't know all the stresses. We just know the stress in the concrete. We don't know the stress in the compression steel. We don't know the tensile strain in the steel. We don't know it. Which means all of these normal forces, we don't have it yet. The internal force, we don't have it yet. And when it comes to external forces, we have just the eccentricity, but we don't have the external force itself. If I'm able to find out the C value, which is this value here, if I have this, what's going to happen? I'm going to be able to find out the strain in the compression steel and the strain in the tension steel from symmetry of these two triangles. Which means finding out C is going to help me out to find out the strains, and therefore is going to help me out to find out all of these forces. So all of these forces I can put in terms of C, and this gives me the direction I'm trying to do here. To find out C1, which is the compression of the concrete, the 0.85 times F prime C multiplied by 0.85 times C multiplied by the width, meaning that C1 is going to be a function of C, which is the neutral axis depth. And this is exactly what we have in this equation. So I have the first compression force in terms of C, neutral axis depth. Now, if we just assume here that the strain in the compression steel is yielding, what's going to happen? This is going to be an assumption that I need to go back and confirm it. If I assume that this here steel is yielding, I'm just going to be taking this AS multiplied by Fy and subtract the cross-section area of the concrete out of it. Some people would find that this is not really critical and just leave it there. Because look at this. You're saying here 3 times 60. And how much are you subtracting? Like 12 out of it. So someone's going to say, no, this is not critical. Others would say, no, this is critical. Let's do it. But this is the correct way of doing it. But I want you to know that some people will just ignore this term here. I wouldn't ignore it. So C2 now numerical value. C1 is going to be based on this C lowercase. And the tension of the steel is going to be tricky because the tensile steel may not be yielding. We have done this previously in the past when we have this compression steel, and then we said we can put the tension steel in terms of C. We have done this equation before. Do you guys recall this equation? Yes or no?
Yes.
Okay, you guys have seen this equation before, right? The way that we are able to come up with this equation by putting the tension force is going to be equal to AS times Fs. Fs here is unknown, it's not Fy. And Fs is going to be equal to this modulus multiplied by the strain in the steel. So, okay, yeah, I understand this. This equation makes sense. Yeah, take Fs is going to be equal to the strain multiplied by Es, the modulus plasticity. And from symmetry, I have this equation between, or this relationship between the tensile strain and the neutral axis depth. This is based on these two triangles. This is going to be one of them, and this is going to be the top one, the second one. So I should be able to find out the strain in the steel in terms of C and D. And this epsilon C is going to be the 0.03. I can take this epsilon S and plug it in this equation here. So tension force is going to be equal to the ES, 29,000, multiplied by AS, which is right here, multiplied by the strain in the steel. And here's the strain in the steel is going to be this box. Can I take it and put it right here, which is this box here, which is the same as this box. This one, see? This is exactly the same. D minus C divided by C multiplied by 0.03, which is the strain on the concrete. So now I have this equation here. If you like to use this equation, then you have the depth, it's going to be 17 inch. You have AS, and you have this constant, the 87. You're going to end up with the tension force is going to be in terms of C. So now I'm going to have only one unknown, which is this C. Now let's go back here. Now I'm going to have all the forces. The C1 and T is going to be in terms of C. And C2, I assume that's going to be yielding, and I have here numerical value for it. So all of this force is going to be in terms of C. I guess I can repeat exactly what I have done here in the balanced point. I'm going to say, let me do here summation of the forces in the x direction equal to 0. I have here the external force equal to the total compression subtracting the tension force. So external force is going to be equal to these two forces subtracting this. Okay. The first force is going to be a function of C. Second force, numerical value. Tension force is going to be also a function of C. So I have here one equation in terms of C. I also can do exactly the same thing. Take the moment right here. Take the moment, right? This is going to be this now the second equation. Take the moment right here about the tension force. You're going to say Pn multiplied by, I'm going to say this is going to be 5 plus 7 inches. It's going to be 12 inches. It's going to be equal to C1 times Z1 plus C2 times Z2. Another equation. Now I have two equations, two unknowns. I can solve for C and Pn. Now it's going to be math, right? I was able here to find out that the C is going to be equal to 1486, and here's the Pn. This is not Pn, this is going to be Pn. Now I need to confirm the strain that I assumed. I assumed that the strain at the top is going to be beyond the yield point. This is why when it comes to this second force, the 169 is going to be based of 60, okay, so I multiply by this AS. Now let me try to find out here the strain. The strain in the tension steel turned to be very low, like what expected. Yeah, this makes sense. And the strain in the compression steel, if you'd like to check here the assumption, it's going to be 0.024. At T, it's going to be 0.027. It's good. So my assumption was correct. How about the phi factor? You can say, now let me find out the phi factor because I have just here Pn. How about phi Pn? The tensile strain, as you see here, is going to be at 0.02, very close to it, right? 0.02. You see this? I'm going to say it's going to be in the left side. Let me not say close to it. So it's going to be in the compression control zone. In this case, the phi factor is going to be 0.65. Now I have phi Pn. Now looking for the moment. Moment is going to be equal to ppm multiplied by E. And my E value was right there. You see this 5 inches? Just multiply here by 5 inches. So take this, the axial force, multiplied by 5 inch, divided by 12. With that, I have phi Pn. With that, now I have 3 points that I have been asked for. The point of 5 inches, the point of balanced point, and the top point, which is right there. Questions? No questions?
For the balance condition,
Yes.
how did you know it was you did 7 plus EB? How did you know it was 7? Just because it's the half.
The mid height between the 14.
Okay.
Like in this case, you see here's 5, here's 12. Why? Because this is here's gonna be 7 inches. Good question. Thank you. This is gonna be here 7 inches. Right? From here to there. Now let me go here to the balance point. From here to there is gonna be 14. Half of it is 7 inches from here to that point. So I can say that this here 7 inches.
So the balance point will always be half.
No, the eccentricity is measured from the middle. This give you the bottom line. You see here, this give you the balancing condition, and this EB is measured from the center of the column, from the middle of it. When you go to the previous case, which is at 5 inches, also this is measured here from the mid height of the column. It's gonna be 7 inches. So the usual eccentricity is measured from the center of the column. Let me go here. You see this 5 inches is measured from where? Center of the column. Let me go back here to this example. You see here where's the E is measured from? Center of the column, the middle of the column.
Okay.
Yeah, any eccentricity, according to this picture here, this P is gonna be at E from the middle of the column.
Okay. Okay.
All right, very good. No problem. Thank you. All right. Looking here at this interaction diagram, I don't think that any one of you guys is going to be interested in doing this by hand. It's going to take some time. But also, I'd like to understand this point. One of the critical points is going to be this point here. This here, when you have no axial force and you have just this section and you can solve for the moment capacity width. Yeah, we understand that. But this is generally is going to be generated by a computer software, or maybe by charts, ready-made charts for you. We have this example, concrete column 24 by 24, 5,000, 8 number 8, grade 60. Here is AS, PPN, and we have done this before, right? This is going to be the previous example that we went through. This is going to be the interaction diagram if you put it in the software. So I'm saying this is going to be my example, right? That I have done previously, and I have done this exactly in the previous lectures. And what I'm going to be doing here, I'm just going to put it in the software and develop this interaction diagram. It's going to come by itself like this. And some significant points is going to be given to me, if you like. Is it okay? When the moment equal to 0, where is that point? Can someone help me? Is this here? Is this where the moment is equal to 0?
No.
So where's the moment? It's gonna be here.
Yeah.
So it says here the force is gonna be equal to 341.5, but I'm looking here is like 1400. So what's wrong? Oh, this at the bottom. So this give you like the tension. Let's give you the tension. Let's give you the tension capacity. I can just look it up from here. I'm going to say about maybe 300 and a fraction. I understand that. But from this table, it's going to be 341.5. Negative here doesn't really means that you're going to have a negative value. It means compression. No, it just is giving the opposite sign. How about the compression? You can see compression also in the moment is going to be equal to 0. It's going to be this point, 1456.3. It's going to be this point here. Small eccentricity. This is going to be good as long as the moment applied to the column. It's going to be about, look at this point here, I'm going to say maybe about 200 kips foot or kip foot. As long as the moment on the column is going to be within 280 kip foot, PPN should be fine, which is this point here. This is going to be 0.15. Then you have some other points here in the middle. If you look at this, some other points. If I give you here some moment demand and axial force demand, I want to see if this is going to be okay or not, right? So let's try the following. I'm going to say in this case, I don't know exactly where this point is going to be, but I'm going to say here PU equals 600 kips. And M sub U, the moment demand equals 600 kip foot. Is this column okay? You think that this column is going to be okay with this given two load combinations, 600 kips, also at the same time I have 600 kip foot? And where is this point is going to happen?
It's gonna be good. It's
600 and 600. It's going to be right there, right? Correct? This within the envelope. This is good. I have no problem with this. Let me try another one. P sub u equals, it's given to me as, let's say, 400 kips. M sub u equals 750 kip foot. Do we have Faris? Is Faris there?
Yes, there.
Okay. Is this going to be okay for this column, or this is not good combination?
What point exactly?
This one.
For 400.
This is going to be bad or good? Is the column safe or unsafe in this case?
It looks safe.
It looks safe?
Maybe.
Okay. All right. Thank you. Thank you, Faris. So M sub u is going to be 750, which is going to be almost here. And P sub u is going to be about 400. Let's say maybe about here. This is completely out of this envelope. So this point is not good, right?
Right.
Okay. Another question. I have a given axial force of 1200 kips. How much is Vmn? How much is the capacity in this case in terms of moment? What is the maximum moment that this column can support if you have 1200 kip foot as a point load, axial load? You say now, let me take it this way, from 1200, draw a straight line. Now it hits this envelope. You take it from here, draw a vertical line. How much is this? Let's say maybe 425, something like that. This is good enough. You can say up to a moment of 425 kip foot, your column should be good. And this is give you the answer for this. Another example. The given moment on this column, let's say here's M sub u equals 300. Let me make it here 200 kip foot. How much is the maximum axial load that this column can support? Let me try this. Can I take this 200? Here's the 200 from here. Draw a vertical line. Kind of interesting because I have 2 points. One is going to be here, one is going to be there. So I'm going to say, let me work first on this point here. How much is going to be the axial compression force? You can say in compression, this column is going to be able to take 1456.3 kips. How do I know it? Because I know this value here, 1456.3 kips. And also in tension, so I'm going to say this here is giving compression, right? How about in tension? VPN, how much is VPN in tension in this case? You say VPN in tension, I can just draw here a horizontal line. How much is this? Let's say if this gonna be 300, how many segments do I have? 1, 2, 3, 4, 5. 300 divided by 5 is gonna be 60, it's gonna be 120. So I'm gonna say with that, I'm gonna have here 120 kips as intention. So actually in this case, I have two values, right? I have one value for the compression and one value for the tension, for the tensile strength of this column. Does it make sense?
Yes.
Okay. You need to see something like this in your second midterm and also in your final. You're going to see something very similar to that. That I'll give you here, interaction diagram, and then ask a few questions. What I'm going to say, if there is no axial force at all, and this is going to be treated as a beam, what's going to be the maximum moment that this beam can support? Can someone help?
300.
Exactly. It's going to be this point. When I have no axial force, how much is the moment that you can apply to it? It's going to be 300 kfoot. Very good. So what is this? It says here mx and my, which means I can have here biaxial column. In a biaxial column, you can have moment in both directions, mx and my. So in this case here, at this given load, I have mx and my. So this is going to be kind of a little bit different interaction diagram. But let me explain this to you. We call it in this case interaction surface. On this axis here, which is a z, this is going to be the axial load. So axial load is going to be going up like this. And this is going to be moment in the x direction, moment in the y direction, and this is going to be the envelope. So instead of having one line like this, we can have a surface. And in this case, we have axial load, and then we have moment in both directions, in the x and in the y direction. This piece here, which is below the surface, is going to be actually in tension. This makes sense, you guys. And yours is going to be much smaller than the one in compression because concrete is good in compression. So if you look at this one here, this is going to be like the part in tension, which is going to be the small piece. And this part here is going to be like the balanced condition, if you like. In this surface, the balanced condition is going to be right here, along this surface here. And this piece here of this shape, which is cut off, this here represents the small eccentricity, right? And again, this piece, which is below the surface, is going to be the tension zone, if you like. Now the combination is going to be between mx, my, and axial load. So this section that you're looking here at is going to be like a section through this, right? It's one of these sections. At an axial load of 1176 kips, now you have all the combinations between mx and my is going to be falling within this range. You should be fine. So here, instead of having just axial load and moment, you're going to have axial load and moment in the x, moment in the y. We call this biaxial, which means that you have x, you have moment in both directions, x and y. This is just for you to understand what's going on, because someone's going to say here, how about when I have a column at the same time exposed to mx and my? What's going to happen? We're going to say, well, also the software is going to be able to develop this interaction surface for you. But we're not going to have any examples or numerical examples on it or questions on it. But this is just for your knowledge, for your information. Besides the computer software that can develop this interaction diagram for you, we have also these charts pre-made for you, and you can have it in lots of textbooks. This is taken here from a book called CRSI. You're going to see lots of charts like this. So you're going to have a round column, or you can have rectangular column, and then they give you this, let's say this interaction diagram, and then you're going to say this is here made for concrete equals to 4,000 ksi, steel of 6 ksi, and gamma of 0.8. Now what is gamma? Gamma is going to be the ratio between the location or the center of the rebar, from center of the rebar to center of the rebar, this diameter, to the big diameter of the column. So gamma is going to be equal to this gamma h divided by h. If it's going to be about 0.8, you can use this chart. If you don't like this chart, you can search for another one when gamma is going to be equal to 0.9. Or here when gamma is going to be equal to 0.7. So you have different values, lots of other charts. How about number of bars? They say we don't care about number of bars. How about the size of the column? They say we don't care about the size of the column. This works here with all size of columns, as long as gamma is going to be equal to 0.8, and concrete strength is going to be 4K psi, and yield strength is going to be 6K psi. This factor here, or normalized moment, is going to be including the size of this column, and so forth. Also this one, which is this Kn. So what is Kn? This is going to be equal, or K sub n, is going to be equal to P sub n normalized to F prime C times Ag for the concrete. So it is normalized. Instead of having numbers, like in our case here, having 1800 kips or 500 kip foot, instead of having this, now we're going to have it normalized as from 0, let's say, to 2. Same thing for the moment, from 0 to 0.35. Now, what is this factor? This factor is going to be equal to the actual moment, which is Pn times E, divided by F prime C, Ag, cross-section area of the column, multiplied by H. What is H? This diameter. This is going to be normalized. So this is going to be a moment, and this is going to be axial load, but divided by a certain factor. Also, you should expect something like this in your exam, because I cannot ask you to develop an interaction diagram in the exam. So instead, I can give you interaction diagram and ask you to use it to solve some problems. We have an example on this. It says determine the moment capacity of the given circular column, axial load demand 540, F prime C 4000, and Fy is going to be equal to 60,000 psi. I have 7 number 8 bars. This is going to be 1 1/2 of an inch cover. This is going to be 3/8 of an inch, which means number 3. I guess you should be able to find out here the value of gamma so that you can pick the appropriate chart. If gamma is going to be 0.8, you're going to be using this. 0.7, use this. 0.9, you're going to be using this. So, okay. Cross-section area is going to be based on this 15, so it's going to be pi 15 squared divided by 4. Cross-section area of the steel, you're going to have 7 rebars. C ratio, right? Because you want to check if it's going to be between 1% to 8%. So we have it here. DS is going to be diameter to the vertical steel. Why do I need it? Because this is how you are going to be determining gamma value. It's going to be equal to 15 inch the total. Subtracting 3 inch, you have 1 cover from here, 1 cover from there, 1 1/2, 1 1/2. Subtracting 0.75. What is this 0.75 coming from? I'm going to say here, you have 1 tie from here, 1 tie from here. 3/8 of an inch, 3/8 of an inch. When you add them, they're going to be 3/4 of an inch. Subtracting 1 inch to the center of the rebar. So someone's going to say, I'm not clear how this was determined. I'm going to say, let me cut a section right here. First, how much is it from here to that point? How much is this, the first distance? You see, this can be 1 1/2, correct? So we can say 1 1/2 inch plus. How about here, the bar diameter? Bar diameter is 3/8 of an inch, 0.375 plus. 1/2 of the bar size is going to be number 8, so it's going to be 1/2 an inch. The whole thing here, you need multiplied by 2, because you have 2 sides. Let's look here. 15, subtracting 3 inch, 1 1/2 times 2, 0.75, 3.75 times 2, 1 inch, which is 0.5 times 2. Take this, gamma is going to be equal to ds, diameter to the vertical steel, divided by h. It's going to be 0.68. So I'm going to say this is going to be very close to 0.7. So let me use this chart of the 0.7, which is this chart. So I'm going to be using this guy here. It's going to be the closest one. Okay, good. So what should we do after this? Now, they tell me here you have PU of 540. And how much is the moment that goes with it? It's going to be very similar to the interaction that we have used, but now I have it normalized. I need to put it in action. So I'm going to say here, let me look at this. If I'm able here to figure out this axial load index, which is normalized axial load. Draw a straight line. Once it hits the steer ratio, you see, because each one of these is going to be for different steer ratio. And my steer ratio based on this analysis was equal to 3.1. I can say is almost equal to 3. So I'm going to be using here is going to be 1%, 2%, 3%. So this is going to be my interaction diagram. If you like, it's going to be this guy here. Right? Like this. So I pick this. This is going to be 3%. Now I need to find out this normalized. So I'm going to say this PN, if you like, this happens when the phi factor is going to be equal to 0.65. For a spiral column, it's going to be 0.75. So I'm going to say P sub U given to me in the problem was equal to 540 kips. How about PN? I'm going to take this number here. I'm going to say PU is equal to PPN. And this phi is going to be 0.75. Therefore, when you put this of 0.75, you should be able to find out PN, which is 540 divided by 0.75, is going to be the 720. So my PN here is going to be equal to 720. F prime C is going to be 4,000. AG is going to be equal to, if you go back here to AG, 176.7, which is right here. Now I can have this normalized axial force index, K sub N, is going to be Pn divided by 4 divided by 176.7. It's going to be 1.02, and this makes sense. It's about 1.02 here. Now it hits this interaction diagram of 3%. Gonna go here with vertical line, and how much is this now? You say this Rn based on the chart is going to be equal to 0.075. So good, 0.075.
I have a question.
Yes.
Where did we get the 0.03 from? Is that for the
steer ratio?
Oh, okay, okay.
The steer ratio is going to be equal to the vertical steer ratio, right? Equal to AS divided by AG.
Okay, okay. I was just
3 point, no problem, no problem. So I find it's going to be 3.1%, so I say 3% is the closest, right? Because next is going to be 4%. So when you compare two lines, you have here for 3%. If I have for 3.5%, maybe I'd have moved and then maybe create my interaction diagram here in the middle, right? But it was very close to 3%, so I just went ahead and I used 3%. Now the Rn, which is this normalized moment, is 0.075. Equals to what? Equals to Pn. Do you have Pn? Yeah, which is right here. Do you have E? No, I don't have E. Do you have A prime C? We have it. Do you have AG? Yes, it's going to be the 176. Do you have H? It's going to be the 15H. It was given here, 15H. Based on all of that, I should be able to find out E. So we can say, okay, let me look at the equation. Here's Rn. Pn, I have it. E, my unknown. F prime C, 4. AG, H. E is going to be equal to 1.1. 1.1 what? Can someone help me with this? Is this inch or feet? Yes?
Inches?
Inches. Yeah, because everything here was an inch. Right? Inch and kips. Now, at the end, the moment is going to be equal to P times the eccentricity. PPN is a 540. Eccentricity is going to be 1.1 divided by 12. It's going to be about 50 kip foot. So this given axial force, I was able to find out the maximum moment that this column can support. Good thing this is recorded, and also is going to be in your exam. You need to see something like this in your exam. Maybe one of these interaction diagrams. Maybe another one that you haven't seen, but available in other books. But they're going to be on the same pages. You're going to have here normalized axial force or normalized axial force in the y-axis, normalized moment in the x-axis, and different steer ratios. And you can just use this interaction diagram. That's simple. If the steer ratio is going to be equal to 3.5%, right? What's going to happen? Let's say my interaction diagram is going to be about here. And in this case, I have drawn this straight line. I'm going to go here vertically down. This is going to be my Rn value. It's going to be close to being here. Did I answer the question, Venus? You're good?
Yes, thank you.
Okay, no problem. Any questions? Another example with the interaction diagram. Same interaction diagram?
Oh no, like maybe something a little bit more, I would say complicated or elaborate.
This is as bad as it gets. But let me tell you this. Let's put more effort on this interaction diagram. You can say for the same column. You can say here for the same column, right? Which means the same 3%. The applied moment equals to